Now we are recording. Thank you.
No problem. Oh, I have a question.
Sure. What's up?
Regarding like the final, if
Hmm.
it's not like how we're doing the quiz, how would you likely like you know how you said that you want to do it like that, but what would be
Well,
another way of taking the
sure.
final?
What I would do is rather than proctor it using Zoom, I would have it open for a day and you could take it anytime during that day. And it would just be very similar to the way that we take the quizzes. Okay.
All right.
So, just during that day, rather than restrict it to that particular time, we would do it that way. Okay.
Okay, sounds good.
You'd have a fixed amount of time. And the reason why I do the fixed amount of time is so people can't rapidly look things up and answer the questions like that. Um,
Mhm.
but I'm sort of toying around with that just because keeping it open all day would probably mean that I don't have to do all these makeups that were so difficult to get people to take. All
Okay.
right. So
Would it
let's
include an
go.
essay?
It will probably include an essay. Yep. So let's take a look at where we left off last time. We talked about the eye and how we perceive light. And again, I didn't spend very much time on this, but we can understand our eye as being actually, it's very similar to a camera. But we focus the light from the outside onto the retina. You have both the cornea and the lens, which work together to help focus this light. The light's focused on, oh, come on, work. The light is focused on the retina, and then we form an image from that. So essentially, we project an image, of whatever outside. We talked a little bit about images onto our retina, and then our retina turns that into nerve impulses that our brain can then perceive. Now, one important thing that we didn't really go into is the different types of light sensing cells which are in the retina. We have some cells which we call rods, okay? And the rods sense only light. They're good for seeing at night because they're very, very sensitive to low levels of light. But the limitation with the rods is that they can't perceive color. That's what these other cells are for. They're called cones. The cones are shown in yellow here. And we actually have three different types of cones: red, green, and blue sensitive cones. And here we can see the rods and cones again. And there's some cones, there's a cone, there's a cone. And then you have many more rods outside your focus of vision. Now, the interesting thing is that you can't see color so well in your peripheral vision. Like when I'm looking straight ahead, I can perceive color very, very well because I have a lot of cones in the center of my vision. As I go off to the periphery of my vision, there are fewer and fewer cones out there. It's really dominated by rods. So my brain plays tricks on me. If I were to have something flash a different color in my periphery vision, my brain would just assign some color to it. I would have to look at it to identify what exactly the color is. So our vision is sort of interesting in that there is a very high definition, if you will, focused part of our vision, which is dominated by cones where we can perceive very fine detail. We can perceive color. This allows us to really examine things up close, okay? Now, this part of our vision we actually call our macula. It is actually depressed in the retina and has a very high concentration of these sensors. As we get away from the center of our vision, again, we can't really form as fine of an image as we could at the center. So again, think about the way that you look at things. If I want to read, I've got to stare straight at that text and place that in the macula of my vision. If I want to perceive, very dark, if I want to use my vision at night, I want to see, in the dark, you probably won't use your macula very much. And, you'll use your entire vision, including your peripheral vision, but that comes at an expense where it's hard to discern what things are. Do you ever notice at night it's hard to figure out what you're actually looking at? Again, that's because you're using your entire vision, which is not well suited for fine detail. Your cones are not sensitive at night. Also, the thing that you lose is at night, unless it's a bright light, you have a very difficult time distinguishing colors. Yes, if there's a bright street light off in the distance, you'll be able to see that color. But if a friend is wearing a different color shirt, perceiving what that color is really, really difficult. Okay. So, again, looking at the retina, this is going to a disease of the retina. Here is the macula. Okay, it's a very small part of the retina. There's the macula right there. And again, that's where most of your fine vision really happens. But again, when we think about our peripheral vision, that's all on these parts of the retina. Okay? And again, through evolution, the way the eye is set up like this is because we want to use the macula for, close-up work. Okay? But we want to be able to perceive threats through the peripheral of our vision. And that's why we don't need as many, rods and cones out there. We just want to see motion. We're not so, we don't really care what's actually on that part of the vision. All right. So, yeah, I could teach an entire course on human vision. But again, think of it as basically an optical system where you have the cornea and the lens, which are going to focus the light. And the retina is sort of like the, I don't know, the film, if you're old school, a CCD, if you want to use a newer technology, where instead of having, charged coupled devices, little transistors that record the light, you have these nerve cells which generate impulses every time light strikes them. Now, one of the problems is that with older people, the eye can run into a number of problems. One problem is, of course, that's very common, are cataracts. And that's where the lens of the eye becomes opaque and it has to be removed and placed with a prosthetic lens. So, cataracts are one thing that we oftentimes have a problem with. Another problem with that older people have, tends to be an older person disease, is what's known as macular degeneration. And in the macula, which has many, many cones to sense light, you can have blood vessels which begin to, I'm not quite sure the reason why this happens, but new blood vessels come in, they start growing in here, they become very weak, they leak blood into the macula. And as a result, what happens is it all actually kills off many of these rods. So somebody suffering from macular degeneration will have damage to the center of their vision, and that really hurts their ability to read. They can still see, okay, but to see close up becomes very, very difficult. And oftentimes what will happen is, in order to make up for this, they'll actually use magnifiers to magnify text and print, so it takes up the entire retina. But macular degeneration, sort of puts a hole in the center of your vision, makes it very, very hard for you to see things close up. And there are treatments for this. One of the treatments is actually to kill off some of the blood vessels. They'll actually use concentrated radiation and hit the macula to to prevent these blood vessels from regrowing and leaking into the system. But that's basically our vision. Now, the reason why I wanted to bring up cones is because it's very much connected to this perception of color that we have. Okay. Any questions about vision before we move on?
No.
Okay. Roy G. Biv, we think that there is red, orange, yellow, green, blue, indigo, violet. I think they just did the indigo because they wanted to make it sound good. In fact, there is no indigo as an official color. Yes, you could, open up a box. I don't know if they still have these Crayola crayons. And they have all these crazy colors that they make up, or you go to, buy paint at a Benjamin Moore store. And again, they have different colors. But officially, there are only 6 colors. And those are from longest wavelength, red, orange, yellow, green, blue, violet, to the shortest wavelength. And the reason why we have these different colors is because this is what we're able to perceive. Our eye has 3 types of cones. One cone that's sensitive in the red, one cone that's sensitive in the green, and one cone that's sensitive in the blue. And by comparing the signals you get from the red cone, the green cone, the blue cone, you can discriminate, roughly between these different colors. And again, here's a look at the visible spectrum. We notice that really the largest part of the spectrum is actually the red part. The red part takes a huge section of the spectrum. Not quite half of the visible spectrum, but a pretty good chunk. Certainly over a third. The next largest part, of course, is green. Our eyes are most sensitive to green light, and that's sitting right there. And here is blue, which is far smaller. Okay, if we only have 3 cones, how are we able to perceive all these different colors? Well, the reason for this is we can imagine, okay, here comes a red photon. All right, hits our retina, and only the red cones produce a signal because they're sensitive to that particular wavelength. Then we get an orange photon of light coming in, okay, or we get orange light coming in. In that case, most of the signal comes from the red cones, but we get a small green signal. With yellow, perhaps the green cones are stimulated the most. A little bit is stimulated in the red, maybe a little bit in the blue. And for green light, again, it probably registers in the red, green, and blue cones, but our green signal is going to be the greatest. Blue light, ironically, stimulates the blue and the green receptors, whereas violet light only stimulates the blue receptors. So basically, when we see these different colors, our eye is comparing the signal from each of these three receptors and trying to place exactly where it is. Okay. Now, here is a curve that shows where our vision is most sensitive. And again, at night when we're dark adapted, probably the only color that we can see well is green. In the daylight, it actually shifts a little more to the yellow, but not all colors are equal. Our eyes are most sensitive to the middle of the spectrum, so we're most sensitive to green and yellow light. And again, here are the different receptors, and the red receptor is not, centered over the red as strongly as we would have thought. Again, only red light will stimulate. Oops. Only red light will stimulate these receptors. Okay. The green and the red receptors are very, very close to one another. And then the blue is way off here. Okay. But that's really how we perceive color. And we actually use this fact that we compare red, green, and blue receptors to generate things like computer screens and other projection systems. All right. If you take a magnifying glass to your screen, you would see a red pixel, a green pixel, and a blue pixel. Okay. Your screen's not actually capable of producing true yellow light. Some actually do that, but a traditional RGB monitor is only going to produce red, green, and blue. So it actually can fool your eye into perceiving a color that's not actually there. Okay, so how do we get white light? White light's easy. Okay, all we need to do is put all the different colors together. We want to project red light. All we need to do is project white light, project red, green, and blue. And the three receptors will be stimulated, telling our eye that we have energy coming from across the spectrum. White light is all light. Of course, if you want to produce a red image on your screen, all you need to do is activate the red pixel. If you want to produce orange, it's a red and a little bit of a green. Yellow is red and green. What happened here? Green is just green. I don't know why there's a blue and a red there. Blue pixel will produce blue. And here's a strange thing. If I turn on the blue and the red pixel, it tricks our brain into thinking that there's violet light there. And violet light is actually a shorter wavelength, but that's how it works. We call these additive colors because by adding three primaries, the red, the green, and blue, we can get the sensation of any color. And again, those two are false. I don't know why that happened there. And again, you're looking at your monitors. If you put it under a microscope, you can see the different pixels as you blow it up. There are subtractive colors, and this is used for printing. When you were in art, you probably learned in school, at least I was taught in elementary school, that yellow, yellow, blue, and red were the primary colors. Okay. Nah, not really. For the subtractive colors, we take three different types of dye. Your printer has in it, if it's a color printer, a yellow dye, a not quite blue, what we call cyan dye, and a not quite pink, what we call magenta. Okay, why do we have these three types of ink when we're printing? Well, first of all, we have to understand how printing works. When we print something, we're starting with basically a white sheet of something. It can be a white sheet of paper, can be white photographic paper. You're just going to want something that's white that's going to reflect any of the incident light on it. Okay? That's what a piece of paper is. Okay. So when I put yellow dye on the paper, what I'm doing by putting yellow dye on the paper is I'm putting a dye which is going to reflect all the colors except for blue. Okay? That gives the appearance of yellow to our eye because our eye will pick up a red signal and a green signal. Thus, we will perceive yellow. What if I want to draw on a piece of paper and produce a cyan color? Okay, so I draw with a cyan pen, and what that chemical does is that will absorb red light, but it'll reflect green and blue light. And the same thing for magenta. I know I'm using different colors. Magenta will absorb green. Now, yellow, cyan, and magenta are called subtractive primary colors because you can put them together in any combination to produce any color that you want. Okay? So here are additive primary colors. Okay? If I add red and blue, I get magenta. If I add red and green, I've already said I get yellow. If I add green and blue, I get cyan. But when I print, if I print cyan plus magenta, I get blue. Why? Because the cyan is going to subtract out all of the red. The magenta is going to subtract out all of the green. What am I left with? Blue. Let's try cyan and yellow. Print cyan and yellow. The cyan gets rid of the red. The yellow gets rid of the blue. I'm left with green. So you can see how this works. That basically your computer monitor, your television, your cell phone display, they all have additive primary color pixels. Okay? They can add the colors in any ratio and display just about any color that your eye can perceive. However, in print, we are not adding light. Okay? Behind your computer screen, you basically have a white light source. For the subtractive primary colors, okay, you're taking away light. That page is originally white. So by using these dyes, we can get rid of some of the light that's shown there. So a little bit confusing, but additive primaries, you put colors together. Subtractive primary colors, use dyes to subtract the colors away. Questions about colors?
No questions.
No questions. I'm just glad you explained the way the printing works because I always wondered how that worked.
Yeah, I mean, the printing's kind of cool because I have one of these cheap colored bubble jet printers, and I'm always having to fill up the yellow and the cyan and the magenta. There's also there's actually two black reservoirs too, just to, you know, increase the amount of absorption. But yeah, that yellow, cyan, magenta, from those three dyes, you can produce just about any color that your eyes can perceive. And again, you know, looking at the computer screen, it's just sort of the opposite of that. So, yeah, and laser printers, if you use laser printers, they'll have a black drum, a yellow drum, a cyan drum, and a magenta drum. And you just have to go through it. You know, every extra color that you have, you know, is extra that the printer has to print. All right. The dispersion. Pretty rainbows. That's dispersion. Okay. Dispersion is an effect where when we send light through a transparent medium, remember I said that light slows down when it goes through glass, light slows down when it goes through water. Well, with dispersion, the color of light, the frequency of light will actually go slower for shorter wavelengths than it will go for longer wavelengths. Okay, let's take a look at some of these. What I have here on the left-hand side, so I have the refractive index, okay? Remember, with a higher refractive index, the light is going to go slower, okay? If I graph the refractive index as a function of different colors, I notice something very interesting. Now, first of all, just for perspective, I want to show you where we are, okay? This, sort of the blue and violet end of the spectrum, okay? And this is a red end of the spectrum. And in between, of course, we have the different colors. Like right here is green, and then we got yellow. Those are the only colors I have to draw with. Okay. What we notice is that, again, for shorter wavelengths, the index of refraction is higher. Now, for some materials, oops, why did it go away? For some materials, like this fluorite crown glass, the dispersion curve is kind of flat. Yeah, blue light goes a little bit slower than red light, but not by a whole lot. Okay. Borosilicate glass is really one of the most common forms of glass. And again, a little bit slower for blue light and violet light, but not all that much. As we get to these higher index glasses, notice the curve becomes more and more extreme. Okay. Now, this case where the speed of light is going to be different for different wavelengths is called dispersion. The reason why we call it dispersion is because if we send the light through a prism, it's going to break it up into its different colors. Okay? So looking at this, we send our light through a prism. Usually we want to send it through flint glass, which has a higher index of refraction to begin with. And you notice that refraction is the property where light bends. But because the index of refraction is not as great for red light bends at a little less of an angle than, let's say, blue light. Okay? It's not all that much, but it's enough where the colors can spread out. In fact, Sir Isaac Newton did a lot of work on this, and he hypothesized that light was actually made out of individual light particles. He never really went anywhere with this idea, but clearly you can see that. Sorry about the sleigh bells. Somebody's moving something in the background. But clearly you can see that as the index of refraction is different, the angle at which it's going to be bent is going to be also different. okay? And again, you can see here a painting of Sir Isaac Newton with his prism. It doesn't disperse the light quite that much, but this effective dispersion is actually very, very important because it allowed scientists to break up the light into its different components and create the first spectrographs. Unfortunately, dispersion leads to a problem when we're looking at things. And this problem is known as chromatic aberration. Galileo's first telescope was abysmal compared to today's telescopes. When he looked at different things, due to the fact that the light would focus slightly different, you would get a blue edge on everything that you're looking at and a red edge. And this was because red would focus a little bit further away than blue would. Okay, I'm exaggerating here. Blue would focus closer and red would focus further. So you could never have all the colors completely in focus. And inexpensive telescopes and microscopes, they all suffer from this chromatic aberration. Optical engineers have figured out a way to get around this problem by using different types of glasses with different dispersion properties. And one of these ways to do it is to use a low index glass with a high index glass. And this is what's called an achromat. Achromat, A meaning without, chromat, talking about without chromatic aberration. And here we can see one of those types of lenses where they've cemented two different lenses of two different glasses together. And by using the different dispersion curves, this brings the red and the green, the red and the blue focus points close together. The green's still a little bit off. By using 3 lenses, you can eliminate even more chromatic aberration. This is called an apochromat. But as you add more lenses, you're just adding more cost to the system. So really, really good optical systems that we find in cameras, that we find in telescopes and binoculars. The cost is really because we're using so many different lenses to get rid of things like chromatic aberration and spherical aberration. Rainbows. Here's an interesting application of dispersion. Inside a raindrop, water does have a different index of refraction for different colors. When we're looking at a rainbow, we're actually looking at falling raindrops. And these raindrops are reflecting the sunlight back to our eyes. If you ever look at a rainbow, you'll notice that the rainbow is always on the opposite side of the sky from the sun, okay? On one side of the sky, you'll have the sun, and usually the best time to see a rainbow is early in the morning or late in the evening. And on the opposite side of the sky, you'll have the rainbow, the red. Now, a rainbow is actually a complete circle, but we're almost never able to see the complete circle because the rest of the circle would be below the ground. What happens here, let me get is that the sunlight will travel from the sun, hit the falling raindrop, and then that raindrop will deflect the light to our location. Draw a little person here, where we will then see it. Now, the reason why we see different colors is the rainbow has to be just at the right angle for that color. The raindrop has to be at the right angle for that color in order for us to see that particular color. So green light will have a slightly different angle than the yellow light, and therefore will appear to be at a different position in the sky. Not very much, but enough to see. Same thing with the blue light. Now, what's important to understand here is that the sunlight is hitting the raindrops, okay? And even if it's not part of the rainbow, those raindrops are still sending that light off at different angles. It is only the angles which match your location. Oops, that's not good. That we will see as being a rainbow. Okay? And again, you can see how the light's a little bit complicated, how it moves inside the rainbow. It enters the front face of the raindrop, hitting the back wall right here, bounces off of that, and then diffracts out of there. Now, you're probably used to different artistic representations of raindrops that make them look like this. They're not teardrop shaped. A teardrop is a drop initially falling. Raindrops are fairly spherical, or if they're falling fast enough, they're, a little bit of an oblate spheroid, but they're essentially round. We can think of them as being effectively round prisms. So again, when we're looking at the raindrops, there's actually rain falling all over the place. The rain's falling down this way. Okay? But again, only those raindrops which line up perfectly with our vision are the ones which are going to produce the different colors that we see. Okay? Now, here's something that's interesting. We see the main rainbow right here. All right? But you also see in this image a very slight rainbow, which is actually backwards in order. Okay? Now, in the raindrop, if it bounces off the back once, we get that primary rainbow. If it bounces off the back multiple times, then we get these secondary rainbows. Okay? Now, the reason why these colors are more spread out and reversed is because as the light comes in, okay, bounces off the back wall twice, and this double reflection actually reverses the order at which the light comes out. So red goes off in this direction, blue goes off in this direction, and green goes off in this direction. And again, you can see how it's reversed. All right. So that is called a secondary bow. All right. Any questions about rainbows?
Is there really gold at the end?
I knew somebody's going to be sarcastic. Not that I have found. Ooh, but that brings up a good point. That brings up a good point. Yes. There is no end to the rainbow. When you're looking at this, and if you try to walk toward the rainbow will itself will appear to keep moving away from you, because again, it's really just an optical effect. You're seeing raindrops, or you're seeing the light reflected off of the raindrops. As you move toward those raindrops, you're going to change the angle that the raindrop is with respect to you. So you'll actually start seeing raindrops further away, which match the angle condition. Okay, so no rain at the end of a rainbow. But what's interesting, here's another interesting thing. We don't see the full circle of the rainbow. If you're up in a plane and you're looking down, you would actually be able to see the full circle of the rainbow. Wonder if I could find, I'll try to pull up a picture of that sometime. But the lower the sun is in the sky, the more of the rainbow you can see. All right, here's another interesting effect. It's a very rare thing, but this is also an effect of dispersion. There's something called a green flash. It's not actually a flash so much. I think they used it in the Pirates of the Caribbean and showed it as a flash. It's not. But basically, when the sun sets, instead of being a nice circle, as we perceive it, as it gets lower and lower in the sky, it appears to be more flat. And that's due to optical effects. That's due to basically the index of refraction of the air. As the sun's passing through more atmosphere, it's refracted more, and that actually squishes the sun down. Oh, by the way, it looks like the sun and the moon are bigger when they're closer to the horizon. They are not. That is an optical illusion. As the sun or moon gets closer to the horizon, your eye can now compare it to things that it understands the size of. You know, it'll compare it to trees, it'll compare it to mountains, it'll compare it to buildings. So with a point of reference, the sun actually looks bigger than it should be. The moon looks bigger than it would otherwise be. But when it's up in the sky by itself, we have nothing to compare it to. So our brain actually makes it, look smaller. You can do a test where, don't stare at the sun, but look at the moon sometime and hold a coin up and compare it to when it's near the horizon to when it's up in the sky. You'll see that there's no difference in size. So the only optical effect that we get as the sun sets is that refraction causes it to appear to be somewhat squashed. Now, the reason why it appears red near sunset, in some cases, rather than sort of a yellowish white, is because as the light passes through the atmosphere, blue and green light are scattered away. So the dominant light that makes it through is the red light. Okay. There's also dispersion due to the atmosphere. So as the sun is setting, the red light is bent less, whereas other colors like green are bent more. Now, there's a very rare phenomena I saw it once called the green flash, where as the sun sets, the last part of the sun that disappears is greenish. Okay, because that light is refracted the most. We don't see blue because blue is so heavily scattered out of this. Then you can see in this, there's a little bit of yellow right here, and red is diffracted the least. So it sort of produces this multi-layered appearance. Okay, so that is what is known as a green flash. And they call it a green flash because it only appears very, very briefly. This is an interesting green flash. Most of the sun is set. All that's left is the green top part, which is being most heavily diffracted. And this photographer actually was able to see even a little bit of a blue glow at the end. So the little bit of blue light that did make it through the atmosphere was preserved. So, interesting effect. All right. So Any questions about our chapter on light before we leave?
No.
All right. Just a few minutes then. Our next chapter is going to be a brief coverage of the atom and elementary particles. And, again, as I said at the beginning of today's session, we only have 2 weeks left. So however far we get, that's how far we get. I know the syllabus has us covering more material, but I'm not going to push it. I'd rather have quality rather than quantity. In this chapter, we'll go over a history of elementary particles. We know that the atom is made of protons, neutrons, and electrons, and we'll see where this basically came from. These ideas came from. And then we'll go into some of atomic spectra. We talked a little bit about producing light from atoms. The Bohr model of the atom, which was the first attempt at applying quantum mechanics to an atom, relative size of atoms, and just a little bit about quantum mechanics and where it came from. So I've got 10 minutes left of class. Let's see how far we go. So the atom, the term atom actually has its origins in ancient Greece. There are two groups of thought with matter and, with mathematics. Some mathematicians didn't believe that infinity could exist, that this concept of infinity was absolutely absurd. So they came to this very strange philosophical conclusion, which, as strange as it was actually correct, that if you keep chopping matter into smaller and smaller pieces, eventually you'll arrive at something that can't be divided anymore, because according to the Greeks, you couldn't continue on for infinity. The concept of infinity was not something that they would accept. So that's sort of an interesting idea, that you cut something in half, then you cut the half by half again, then that half again. They figured that you couldn't go on doing this forever, and therefore you had to come to a stopping point where matter couldn't be divided into anything smaller. And that was this idea of the atom. Now, there was this philosopher around 530 BC who made this argument. It's not clear whether he was the first to make this argument, but he's certainly given credit for coming up with the idea of the atom. Leucippus should also be noted here, because some argue that he was the one who came up with his first concept of an atom. But our biggest problem with a lot of this ancient Greek philosophy is that not much of it was well documented. A lot of it was passed on from person to person. So, people like Pythagoras, people like Democritus, Leucippus, maybe they were responsible for these ideas, or maybe they were simply responsible for passing these ideas on to the next generation of philosophers. Now, unfortunately, for this idea of the atom, other philosophers such as Aristotle believed this atomist model of an atom was not true, or did not have a logical basis. And the idea was pretty much left forgotten until we got to the time of the Renaissance. Robert Hooke in 1665 really started wondering about the structure of crystals. Crystals had a very definite organization to them, very definite shape to them. And he hypothesized that the only way that we could arrive at, a certain shape for quartz crystals, a certain shape for salt crystals. Especially we look at salt. Salt always has this cubic structure to it if we grow crystals. He argued that if matter was made out of these hard spheres could only pack themselves in a certain way, which would lead to these large macroscopic crystals. So Hooke was really the first to, rejuvenate this idea of the atom, making the argument that crystals would owe their shape to the way that these hard spheres would be packed. So in Hooke's model, of course, the atom was a hard sphere that would, stick to other hard spheres, and from that we would get crystals. In 1807, John Dalton used chemistry to argue for the existence of atoms. He noted that only certain chemicals would react with one another in only certain ratios. We know, of course, 2 parts hydrogen interact with 1 part oxygen to produce water. 1 part carbon interacts with 2 parts oxygen to produce carbon dioxide. Carbohydrates are carbons with, a certain number of carbons, twice as many hydrogen to oxygen. And again, he had no other physical proof of this, but he argued that, there must be different types of pure substances, these elements, which were made of only one type of atom. So after Dalton's work of the atom was just viewed as being this small, indestructible sphere that you really couldn't do anything with. The atom is what it was. Hydrogen atom would always be a hydrogen atom. An oxygen would always be an oxygen. Carbon would always be a carbon. With Dalton's work, basically, any further understanding of the atom was put on hold until the late 1800s, where Jean Picard witnessed a strange glow. It's sort of similar to St. Elmo's fire, which is viewed during lightning storms. But he was watching the weather, and he was watching a barometer. He noticed a strange glow from the vacuum, which was sitting above the mercury reservoir, and this light blue glow seemed to appear with the waxing and the waning of the storm outside. Picard had no idea where this came from, and we know today it probably came from static electricity from the surface of the Earth and the electric fields that were being set up during this thunderstorm between the surface of the Earth and the sky. But this inspired other people to investigate vacuum tubes. Again, the barometer was used to measure the pressure outside. It was created by inverting a reservoir of mercury, and the weight of the mercury pulled down and create a vacuum above it. In 1870, Williams Crook perfected this effect by artificially introducing electricity. And he created a Crookes tube where on each side of the tube, you would have an electrode. And by setting up a voltage, on one side you connect a negative charge, on another side you connect a positive charge. You could force electricity through this tube of very low pressure gas. Basically, their vacuum pumps weren't very strong in the 1800s. So there'd still be some gas left over, but the pressure would be low enough, the density of the gas would be low enough that the electricity could flow through. And again, Crookes was able to demonstrate glowing gas in these tubes, similar to what Picard had had demonstrated during his lightning storm. Further modifications to the tube showed that whatever this glow was being caused by, we could cause the sides of the tube to glow as what now was perceived as rays of energy. They were called cathode rays, would bump into the glass sides and cause the tube to glow. Usually would give off a greenish glow. And that's because back then the borosilicate glasses would have a resonance in the green. But what they did with these Crookes tubes, or what Crook did with these tubes, is showed that these rays would emanate from the cathode. Okay, so they must be negatively charged, and that they could cast shadows. But again, nobody really knew what they were. They placed them in magnetic fields and showed that they could be deflected. Again, indicating that the charge was negative. But it wasn't until J.J. Thomson in 1894 that he was experimentally able to demonstrate that these rays were moving slower than the speed of light. Already it had been established that these cathode rays were negatively charged. And although Thomson was able to obtain a relationship between the charge and the mass of the particles within these rays, he was unable to get an exact value for the charge or for the mass by itself. So he had a ratio, excuse me, of the two. All right, got to stop right there. Yes, thank you. Again, we'll continue with this. Thomson is discovering the first part of the atom here, and that's the electron. And this had profound impact on the model of the atom that we would then develop. Okay, folks, so we'll end it there. Since I am out of time, let me stop the share. I will stop the recording.